clear understanding about quantum information. I've always found his talks very illuminating. You can always learn something from his talks. Now, so I will not, you will judge him, and he's our nearby neighbor, SM Bose Center. He was earlier in ISER Tiruvananthapuram. He has been in this, quantum information theory for quite some time. So the stage is now to Manik. I will not add any more. You judge Manik on his own merit. Okay.
Am I audible?
Yeah, you are audible, and it's also visible. Make it full screen if you want. Yeah.
Okay, sure. Just a minute.
Yeah, you can start. Yeah.
Just a minute. I'm just
sure.
Make it full screen.
You can take 10 more minutes, no problem. Huh?
Okay. Is it now full screen? Hello. Okay. So good day, everyone. So first of all, I would like to thank Professor Banik and the organizing committee to ask me to give a talk here. So today, the title of my talk is Classical Superdense Coding and Communication Advantage of a Single Quantum. I'll gradually explain what do we mean by superdense coding and what we try to introduce. It's called classical superdense coding. Gradually, I'll try to introduce it. So before going to the technical part, just some few formalities. I have to acknowledge the funding, means all the agencies who supported us for doing research for last few years. Hello. I'm in a meeting. I'll call. Who is this? So these are my funding agencies. So let's try to motivate. So information processing and communication tasks are every day present in our daily life. Like what now I'm talking to you through a internet. This is a communication process, and this development of quantum information theory. After that, people try to come up with new information theory tasks, some of which are advantageous over their classical counterpart, and in some case, some of them are actually impossible in classical part. And why people try to come up with new tasks? First of all, one simple answer is these are advantageous. Another approach, another answer is all these tasks actually help us to understand difference between quantum and classical theory. We'll see that actually this information theoretic task or communication task actually helps us to understand or differentiate between different resources. These resources could be classical resource or quantum resource or mathematically more general kind of resource. This is sometimes called beyond quantum theory. Okay, and for that we will introduce some toy setup. Why will we introduce toy setup? Because these toy setup are very generic. They can encompass any theory. It could be classical, quantum, or beyond quantum theory also. And then we will compare this resource strength. So today we will discuss mainly a communication task. So in a communication task, mainly the resources we can differentiate between two types. First one we call type 1 resource, or sometimes it is called common past resource. What does that mean? You see, this is the light cone. So this is there are two agents, Alice and Bob, and this Alice space-time point, we draw the light cone. So anything Alice can communicate must be within this light cone. Since Bob is in space-like separated, so Bob is not in Alice future light cone. So now what is common past resource? Now if you extend this past light cone of Alice and Bob, now you see there is some overlap region. That means in this region of space-time, Alice and Bob can meet together. This is their common past. At that common past, they can prepare something and share between them, which they will use for communication, which they may use for communication purpose at a later phase. That's why it is called common past resource. Now, what this common past resource could be? We come together. Let's say Alice and Bob come together and share some strategy, like share some coin. Let's say coin is very peculiar coin. If Alice coin is head, at the same time, if Bob tosses the coin, it is also head. So if Alice coin is tail, Bob coin is tail. So it is called shared coordination, shared coin. In principle, it is possible to prepare, but these are classical. But also this common past resource can be beyond quantum, beyond classical also. What is this? You have already heard probably in many talks, quantum entanglement is one such resource. In their common past, Alice and Bob come together and jointly prepare entangled state. And one part now is with Alice, and now another part is with Bob, and now they are space-like separated. So these are called common past resource. It's different type of resource is called type 2 resource, which is called direct communication resource. What is this direct communication resource? Now, in this case, Alice actually encode her information in some physical system and send it in her forward or future light cone. Now, Bob come to in Alice future light cone and hold this encoded particle and try to decode it. So this is actually communication. Now I am talking to you. This is something direct communication is happening. So I am making I'm talking, so the vibration gets encoded in this electromagnetic way, and it gets transferred to you, and then it is decoded, and then you are listening this voice. So this is a direct communication resource, or it is type 2 resource. Now you see, common past resource or type 1 resource by themselves, they don't have any communication utility. We just shared previously, let's say now I want to communicate something, but 1 year back we have come together and create some shared correlation or entanglement. How that could help me to communicate at present? That is not possible. That's why common past resource by themselves own, they are not useful for communication. They have zero communication utility. On the other hand, direct communication resource has utility in communication. Now this is our setup. Alice and Bob, they are space-like separated agent, and they may share type 1 and or type 2 resource. Because type 1 resource alone is not useful for communication. Type 2 resource alone can useful for communication. Now the question is, they may have both these kind of resource, type 1 and type 2 resource. This is our question. Now both this type 1 and type 2 resource, each of them can be further again classified classical, quantum, or post-quantum. So type 1 classical resources, shared randomness. Type 1 quantum resources, quantum entanglement. Type 1 beyond quantum resources, it's called general no signaling correlation. One such famous example is Popescu and Rayleigh correlation. What is type 2 classical resource? One example is just a qubit, 1 bit of communication. A 2-level classical system we can communicate. What is type 2 quantum resource? A qubit is one such example, a 2-level quantum system. What is type 2 beyond quantum resource? There is some mathematical model is possible. GBit is one example. It's called generalized bit. There are lots of different examples are possible. So this is our setup. Now in general, there will be some input and output on Alice and Bob side. Now depending on where we give the input and output, further different scenario we can come up with. The most famous is the Holemo scenario, and more recently there is some seminal work is done by another group of information theory is Frankel and Wiener. That's why we are calling it Holevo-Frankel-Wiener scenario. The relevant reference is given below. So now what is this scenario? In this scenario, Holevo-Frankel-Wiener kind of scenario, Alice is given some input and Bob has to generate some output. And Alice try to encode her input in some physical system and send it to Bob. And Alice and Bob may or may not share different type 1 resources. And finally, there will be some payoff will be calculated depending on this input and output. So this payoff is mathematically in general model as some mapping from this Cartesian product of input and output set to real number. So this is the most general, most basic communication scenario. It is called Holevo-Frankel-Wiener scenario. The next one is, okay, so what is this two paper actually prove very fundamental theorem. This Holevo and Frankel-Wiener, Holevo in 1973 and Frankel-Wiener in 2015. What they prove? They prove that a classical D-level system and a quantum D-level system, if they have classical shared randomness as free resource, then communication utility of these two systems are always equal. Quantum has no advantage. We are learning day by day new quantum advantage, but this is a no-go theorem. This says that quantum, if shared random, Alice and Bob has unlimited amount of shared randomness, then classical and quantum system communication utility is identical. A D-level quantum system is similar to a D-level classical system. So this is the Frankel-Wiener and Holevo theorem. This is called Holevo-no-go theorem. It's a limitation theorem that quantum may gives us lots of advantage, but in this scenario, quantum will not give us advantage. But one important point is crucial point to note here that shared randomness is free at this case. Another scenario is called Wisner, Ambianis, Nayak, Tasama, and Vajirani scenario. Actually, this is called this task is called RAC. It's now popular as random access code, but initially it was proposed by Wisner in 1980s by the name of conjugate coding. Then Ambianis, Nayak, Tasama, and Vajirani rediscovered over it, and they put the name random access code. So what is the scenario? Look into that. The scenario is that in Holevo case, Alice has only input, Bob has output. But in this case, Alice has input as well as Bob has some input. Why? And Bob has some output. Alice has no output. Alice just input and send it to Bob. So this is called Wisner communication scenario. Again, here can be type 1 and or type 2 resources. So there are few interesting paper reference I have cited here. If you are interested, you can go through it. And finally, the most famous scenario, most popular in quantum foundation, is the Bell scenario. In this case, both Alice and Bob has input as well Alice and Bob give output. And in this case, important to note that no type 2 resource are allowed between Alice and Bob. That means Alice and Bob are not allowed to communicate with each other. Okay, this is the three scenario. Now, as I said, Frankel-Wiener and Holevo, they have proved that if shared randomness is free, then classical and quantum are identical for communication utility. Now one can ask the question. So that means what this theorem proves? That quantum type 2 resource, that means direct communication resource is CD or QD. That means quantum type 2 resource QD is same as quantum type 1 resource CD, classical type 2 resource CD, provided that classical type 1 resource, that means shared randomness, is freely available. But if quantum type 2 resource is there, then what will happen? Can we say classical and quantum are identical? No, we cannot say that. There is a very seminal result that is called quantum superdense coding. What it proves? That quantum entanglement can double the communication utility of a, or communication capacity of a qubit quantum channel. So that means Q2, a two-level quantum system, or it can be generalized also, along with entanglement, this is more powerful than a two-level quantum system for communication purpose. But classical level, if you say entanglement and classical communication, that will not increase your communication power. A quantum channel means quantum communication along with quantum entanglement that can enrich your communication power. So this is classical famous quantum superdense coding task, and proposed by, again, in a seminal work by Professor Banik and Weisner. Very recently, some interesting development has been noticed. They have shown that even entanglement, they can empower the classical utility of a classical channel. So dense coding, you try to note that quantum super dense coding is entanglement can empower communication utility of a quantum channel. But this recent result try to show that quantum entanglement can actually empower communication utility of a classical channel. So entanglement empowers classical channel, HSW scenario. All the scenario in this talk we will discuss the basic HSW scenario, because this is the most basic one, basic scenario. So what is our conclusion so far? That means quantum type 1 resource, that means entanglement, can enhance utility of type rho resource, both classical as well as quantum. That is the pictorial it is showing. Type 1 resource, no communication utility by themselves own, but type 1 resource plus type 2 resource that is strictly greater than type 2 resources. So now we ask the question, what about classical type 1 resources? That means shared randomness. Can shared randomness enhance type 2 resources in HSW scenario? This is our question. That means we will ask, instead of shared entanglement, if they have shared classical coil, can there be any advantage if some classical channel is there? We'll answer this question affirmatively. Yes, that is possible. That's why we call it classical super dense coding. A classical type 2 resource, a classical type 1 resource, that means shared randomness, can enhance communication utility of a classical type 2 resource, that means classical channel, perfect classical channel. Okay, for that we will introduce a game. Let us try to understand the game. Very simple game. So game is, there is a Charlie, and Charlie has many students. Okay, lots of chain of students. And each day one of the restaurants is closed. But which one is closed? That is randomly. Charlie decides that randomly. Now, which restaurant is closed? That information is given to Alice. On the other hand, Bob wished to visit some restaurant. Now, what is a rational Bob wish to do? Of course, a rational Bob will not want to go to a closed restaurant. But that information is not with Bob. That information is with Alice. Now, Alice wished to help Bob with some communication channel, and communication channel is limited. Only one bit communication channel is there between Alice and Bob. So what is the rule of the game? Rule of the game is each day one of the restaurant is closed. Which restaurant is closed? That is randomly decided by Charlie, and that information is given to Bob, that given to Alice. On the other hand, Bob wants to visit the restaurant and he don't want to visit the closed restaurant. This is the first rule. Second rule is that in a long run, they want that all the restaurants have same business. So there is no, because if only one restaurant has business, then all the capital will just accumulate there. So you can think it as, okay, they are non-capitalistic minded agent. They are wanting that all restaurants have same kind of business, equal probability. We'll see later part. We'll see even that particular restriction we can generalize. So as I said, the restaurant game rule is that Bob never visit a closed hotel. Bob visit all the hotels equal number of times in long run. So these are two conditions. Using only, and the restriction is that Alice and Bob has only one bit of channel. Now they have to play the game. So now before playing the game, how can they play the game? And again, try to remember that this is the communication scenario we are discussing is actually this Holevo-Frankel-Wiener scenario. Alice has some input and Bob has some output. Means depending on this output, Bob wants to visit some restaurant, and from input output they will accordingly will be given some payout. So now let us try to define some strategy how they can win this game. So we call it CDS, classical deterministic strategy. So what is a classical deterministic strategy? So a classical deterministic strategy, you can think in this way. Classical deterministic strategy is an encoding decoding tuple E and B, where E is a log n bit to 1 bit deterministic function. So there are n restaurants and Alice know this information. Depending on this information, Alice encode this information into only, because there is only 1 bit channel, into 0 or 1. So it is a function from log n bit to 1 bit, deterministic function. And what is D? D is, so from Alice, Bob gets either 0 or 1, and depending on 0 and 1, he decides which hotel he wishes to visit. So it is nothing but a 1 bit to log n bit deterministic function. So a encoding scheme is a deterministic function from n bit to 1 bit. On the other hand, a decoding strategy in this case is nothing but a 1 bit to log n bit function. So this is a classical deterministic strategy, because only they have to satisfy this limitation that only 1 bit communication is allowed in each run between Alice and Bob. So you can generalize a little bit. It is called classical mixed strategy, CMS. What is classical mixed strategy? Now, it is nothing but a probability distribution on Alice encoding strategy times probability distribution on Bob's decoding strategy. So now Alice decides. Alice has many coins, 2 outcome coins, two face coin, 1 coin, first coin, second coin, third coin, so on. So if restaurant I is closed, Alice toss her ith coin, and depending on her coin outcome, she sends the message through the channel. Now, getting this message 0 and 1, Bob has some n level quantum system. N level classical coin. What is n level classical coin? Okay, 2 level classical coin is our standard coin. What is 6 level classical coin? You can think it as a die. What is n level? That means n faces some polytope kind of things. Alice, Bob toss this coin, toss this object. Depending on the outcome, he decides which restaurant to visit. So this is called classical mixed strategy. Is this all? No, actually classical mechanically they can do something more also. For that they require more resource. What is that? That is called CCS, classical correlated strategy. That means apart from this 1 bit classical channel, Alice and Bob have a shared coin. Shared coin means this coin, one part is with Alice, another part is with Bob. Now somebody say, okay, your Alice outcome is 1. If Alice outcome is dead, at the same run, Bob outcome is also dead. That means their outcome is shared, correlated. So some third party actually giving this correlation. In our everyday life, we always face this kind of correlation. When you are driving in a road, you don't know what other person are running. Let's say you are in a crossroad. You are going through this path, another fellow is coming through another path perpendicular. You cannot see. So you both can come and can collide. But it is not happening. Why? Because we are following some shared strategy. What is shared strategy? This traffic signal. That means my one is now red. That means I have to stop. other one is green, he will pass. So some third agent, in this case, third agent is traffic signal, traffic police, they are giving this instruction. So the shared point you can think as like this instruction, correlation. So depending on this correlated coin, they can decide which particular CMS, classical mixed strategy, they will follow, and they will obtain a more general class of strategy. So this is called classical correlated strategy. So what in general we have, it is not only this, not only for this restaurant game. In any general Frankel-Wiener scenario, you can show that CDS, classical deterministic strategy, is always a subset of CMS. Classical mixed strategy is always a subset of classical correlated strategy. So now classical correlated one means we have allowed our now type 1 resources, classical type 1 resources. But we want to see whether it is actually a resource or not. Now, there is a, we'll use this notation Hn 1 upon n. What do you mean by this? Is restaurant game or hotel game? That's why H. We can use the R notation also, but R is generally used for real number. That's why, though we call it a restaurant game, we use the hotel H notation, H index. N means n number of hotel. 1 upon n means all hotel need to visited equal probability. That means H1 first condition, Bob never visit close restaurant, Bob visit each restaurant with equal probability. Now we have defined this strategy, classical deterministic strategy and classical mixed strategy. It can be shown that if n is even, then by classical mixed strategy they can win this game. But if n is odd, then they cannot win this game by classical mixed strategy. So that means only a Sibir channel is not sufficient to win the game perfectly whenever the number of restaurant is odd. But along with this Sibir channel, if they are allowed shared correlation, then they can have perfect winning strategy. So what does it prove? It proves that classical shared randomness can empower a classical communication line. And now this Hn game, it is just a special case where all the restaurant has equal business, but you can actually in principle generalize. Bob never visit the closed restaurant. That means H1 prime condition is same as H1 condition, but H1 condition now you H2 condition now you generalize. That means Bob visit the kth restaurant with probability gamma k. When all the gamma k are equal, that boils down to our this rule. Okay. So you can actually study this 3 hotel game more elaborately. If you are interested, you can go through this, our work. We have studied properly. And this is the game space, 3 parameter, gamma 1, gamma 2, gamma 3. This pink region are the unphysical game, they are not allowed. This green region with the boundary are the allowed game. And you can show that all the game on the boundary of this hexagon region can be won by classical mixed strategy. On the other hand, any game within this green region cannot be won by classical mixed strategy. But if you allow shared correlation along with your classical line, all these games can be perfectly won. Yeah, I see someone raise hand. If you have some question, you can ask in between. Yeah. Is there any question? Okay, if not, let's go further. So this proves what? This proves classical superdense coding. A classical perfect communication line that cannot win this game perfectly, but along with correlation, classical correlation, the game can be perfectly won. Remember this quantum superdense coding. a perfect qubit line, its capacity can be enhanced with quantum communication, quantum correlation, that is entanglement. Here we are trying to say a perfect classical line, its utility can be enhanced by classical correlation. How we are proving that? We come up with a game. The game cannot be win if they have only a 1-bit classical, perfect classical channel, but that classical channel along with shared classical correlation gives a winning strategy for this game. Okay, further, what kind of question we can ask? We can ask this question. Instead of classical line and classical correlation, we only provide only a qubit line. That means a qubit, only a perfect qubit communication will happen. Is it possible to win this game? We answered this question, yes, it is possible. But before that, what is the definition? How to define quantum strategy? So a quantum strategy is an encoding decoding tuple EQ and DQ, where EQ is the log n bit to 1 qubit bijective function. In earlier case, it was log n bit to 1 qubit, but now it is 1 qubit. Qubit is, you can think as its state space is a block sphere in R3. That means you can encode your message in any state of this qubit from the block sphere. And what is the decoding strategy? Now Alice encode her message and send this encoded quantum state to Bob, and Bob is allowed to perform any generalized measurement on this qubit system, and accordingly, depending on the outcome, he decides which restaurant to visit. This is our quantum strategy. Now it can be shown that this 3-hotel equal probability game can be perfectly win if we follow this particular strategy. This psi1, psi2, and psi3. These are Alice's encoding strategy. That means if restaurant or restaurant 1 is closed, Alice will send psi1 state, for B psi2, for C restaurant psi3. What Bob will do? Bob will perform a POVM measurement, and this is a peculiar kind of measurement. It is not a projective measurement. It is a rank 1. Each of the POVM elements are rank 1. It is trine measurement. So this is shown in blue kind of the semicircle. Okay. Now look into carefully this pi1 projector. Pi1 means this pi1 effect, which is proportional to the projector perpendicular to psi1, will never click when psi1 state is sent. That means if Alice sent, if let's say hotel A1 is closed, at that time Alice will send psi1, and Bob will perform this measurement pi1, pi2, pi3. If now you see pi1 restaurant will never click because it is exactly perpendicular to psi1, but pi2 and pi3 they will click with equal probability. And now if pi2 is clicked, pi2 gets clicked, Bob decides he will visit restaurant C. If pi3 clicks, he will decide he will visit restaurant B, like that. Similarly, you can see from the symmetry of this encoding decoding that both these conditions will be satisfied. Bob will never visit a closed restaurant, and in long run, all the restaurants will have equal business. And actually, not only this equal case, you can actually show that all the game, in the game space, all the game can be perfectly win by quantum strategy. For that, accordingly, you have to design your quantum strategies. Okay, so this is 3-hotel game. What about 4-hotel game? As I said, 4-hotel equal probability game that can be win by perfectly. That can be win perfectly with only 1-bit classical communication. But if you can come up with a different game which is not equal probability, you can show that this game cannot be win by 1 bit of communication. But of course, 1 bit of communication along with classical shared randomness, you can win this game perfectly. On the other hand, in quantum world, you can win this game only by a quantum communication. No correlation is required. So this is the strategy. You don't have to worry about for the time being. This is just a calculation. If someone is interested, if you go through it, you will find that it is actually satisfying this game condition. So then we ask this question: what is the reason? What is the foundationally which is required for this quantum advantage? Because why this is quantum advantage? Because in quantum world, to win this game, you require a classical communication line and correlation. But in quantum world, you can win through quantum communication line only. No correlation is required. That's why it is called quantum. We call it a quantum advantage and simplest quantum advantage, because it is the simplest communication scenario using a single quantum system. Okay, so we prove two propositions. First proposition says a qubit is no better than a cbit in HSW scenario for any orthogonal encoding applied by Alice. Now look into that. Try to remember. Alice used this kind of triangle kind of encoding. These encoded states are not orthogonal. You can prove that in this kind of game, if Alice follow a orthogonal encoding, there cannot be any advantage. The success probability will be as classical. Furthermore, if Bob perform a projective measurement, then also this second proposition tells us on decoding end, if Bob performs only projective measurement, then also the advantage is not possible. For that, generalized POVM measurement is required. This indicates towards a deeper foundational implication. Today, I will not discuss here in details, but you know that in quantum foundation, you know that for a qubit case, if we consider projective measurement, then we have a deterministic hidden variable model. The model is given by, first one model is given by John Bell, and then another model is given by Kochen and Becker. Then naturally the question arises, what about generalized measurement, this POVM kind of measurement? Can we give a deterministic model? In 2014, Rob Spekens, he actually proved that no, it is not possible. Even for a qubit 2-level quantum system, if you consider POVM kind of measurement, it is not possible to give a deterministic hidden variable model. Now, in our task, you see, we are proving that to have an advantage, you require a POVM kind of measurement. So now, whether there is a deep connection between this foundational implication is there, we haven't answered this question. We keep this question as an open question, whether this task indicate towards a deeper foundational implication or not. If you are interested, you can have a look into the paper or the question more details. Okay, as I said, these are some, again, I am not going in details. These are some qubit kind of model, generalized probabilistic theory model. In earlier talk, you are listening about this distribution functions. So these distribution functions are in general classical probability theory. You can think it's a probability theory on a simplex. What is a simplex? Simplex is a convex set with finite number of external points, and each mixed point has unique decomposition in terms of its pure state. On the other hand, quantum mechanics is a generalized probability theory. It's a probability theory on a convex set, which is not in general simplex. These are more general. This is called polytope in general. This is not simplex. So this is in general mathematically consistent mathematical model or theory you can build on polytope. So this is one example. This is called n-gon theory. This is 4-gon. Sometimes it is called box world. This is hexagon, and so on. You can in principle consider n-gon, which n tends to infinity will give you the great circle of the block sphere of our qubit. Okay, we have actually shown that using this qubit also we can win this game. So the advantage which is obtained by quantum mechanics can also obtain from this kind of generalized system. Then naturally the question appears, then this advantage is not quantum. This advantage is non-classical in general, we should say. Because not only quantum theory gives us this advantage, another non-classical theory also gives us this advantage. Then we come up raise this question: can we come up with a game where even this GPT model will not give me advantage, then we can say, okay, the advantage is quantum in nature. Neither classical theory nor beyond quantum theory gives me an advantage, but quantum theory gives me advantage. Yes, that is also possible. In this case, your this rule has to, this is a little bit strict kind of game. The rule has to be modified. And if you modify your game, it can be shown that these N1 theories are no good to win this game. On the other hand, quantum can give you a perfect advantage. Okay, so, and we also prove another result also. There are games which, if you have 1 bit of classical communication channel plus 1 bit of shared randomness, the shared randomness that also can be quantified with the same unit bit. So 1 bit of classical communication line plus 1 bit shared randomness, you cannot win this game. You require 2 bit of shared randomness. So more shared randomness is required. On the other hand, in quantum world, only a qubit communication line is sufficient to win this game. So 1 bit qubit line is sufficient to win this game. So in gist, this is our result. So as I said, this Charles Bennett and Wisner superdense coding paper, it shows that a qubit plus e bit is always greater or equal to q. So what do this greater or equal to this equal to? There are different ordering we have mentioned in this chart. Each ordering has different meaning. A is equal to B means they provide same utility in all tasks in HSW scenario. Two resource, if we say resource A is equal to resource B, that means in any task, whatever task you can define, they provide same utility in this HSW scenario. A less than equal to B means there exists at least one task where B is strictly greater than A. So B is as good as A, and there exists a task where B is strictly better than A. And this means A instance B means there exists a task where B is better than A. That's all. There might exist a different task where A is better than B. So now you see this following ordering relation between this type 1 and type 2 resource we can put. Dense coding say Q is less equal to Q plus 1 AB. There is a recent result by Frankel and Weiner. They say that C less than equal to C plus 1 EBIT. If shared randomness is free, then C plus SR is equal to Q plus SR. But if it is not free, then we prove that C is less equal to C plus SR. This is our Hn gamma 1 gamma n game for n for n greater than equal to 2. C less than equal to Q, that is this H3 game, and then so on. So all these medial results, medial order relation are proven by us, and first three and last one is by other ones. So now quantum advantage is established. Now the question is, okay, let's go to lab and try to establish whether it is possible. But for that, we have to make our advantage noise robust. Whether the advantage survive even the encoding decoding is noisy. Yes, it is indeed survive. In this picture, I have given you a very simple kind of model. Your encoding, Alice's encoding and Bob's decoding is if encountered a white noise, or more popularly called depolarizing noise, which is very common, most common noise in experimental scenario, then you can actually derive a threshold of this noise parameter beyond which this strategy show quantum advantages. Not only, but you see, this advantage need not to be depolarizing noise. It could be arbitrary noise. They are also in principle possible to come up with some bound where quantum advantage is possible or not. So with that, let's try to briefly conclude our result. First, we show that SR is not free in HSW scenario. However, Frankel-Weiner scenario, classical shared randomness should not be treated as free resource. although in Bell scenario it is considered as free resource. Why we say that? It is possible to come up with a task which is possible to win with 1 qubit communication, but in classical case it requires so what is the next question we can ask? We have shown that okay, 1 qubit line is better than 1 qubit plus 1 shared randomness or 2 shared randomness. Is it possible to come up with some task where it can be shown that 1 qubit is more advantageous than 1 qubit plus unlimited amount of shared randomness? We don't know. We don't know the answer. But if someone can come up with such a task, it will be quite interesting. So as I said, another question that the advantage we have reported, whether it has a deep foundational implication, we don't know. We put this question in our work. And of course, in principle, the game can be extended for multipartite scenario, because we have considered only a bipartite simplest space. In multipartite scenario, lots of different kind of correlation, genuine entanglement, lots of peculiarity arise. There may be some more intriguing result one can expect there. So with that, I'd like to thank my collaborators, Shahil, Edwin, Shamrat, Ramkrishna. They are my PhD student. Mir is my postdoctoral fellow here, and Tomal or Shom are doing their postdoc. Tomal is now in Gulo Chiribala's group in Hong Kong, and Shom is in Horodoki's group in Gdansk. So with that, thank you all. If anyone is interested, you can look into this work. This is a little bit lengthy work, but every details you will find in this paper. If you find any difficulty, you can write to me or any of our collaborators. Will be happy to answer your question. Okay, thank you for your patience. If you have any question or comment, please, I'm happy to.
Maruja.
Hello.
Hello, sir.
Yes.
Sir, all these work are based on infinite shared randomness. So, is there any advancement in your work in the finite shared randomness? Like you have listed. So,
Yeah,
in this reason,
so when we are saying shared randomness is free, we are saying Alice and Bob can have unlimited amount of shared randomness. That's all. Intentionally, I use the word unlimited. I don't use the infinite, because this infinite is a mathematical concept. So they can have shared randomness as much as they want. That's all. Okay. So what we have shown that a perfect qubit line is better than a perfect qubit. There exists some task for which a perfect qubit line is better than a perfect qubit line plus 1 bit shared randomness or 2 bit shared randomness. But whether a qubit line is better than 1 qubit plus unlimited amount of shared randomness, we don't know. That's why I think this is if someone can come up with such a task, that could be interesting.
okay.
Yeah. Cbit means 1 bit of communication. So you can think as you send 0 or 1 to symbol or in analogous setting high voltage and low voltage, and it exactly goes. There is no noise. It is called 1 bit of communication. It's called classical bit. Short form is Cbit. Okay, I think we are out of time. Any organizer is there? Or
Yeah, I am here. Yeah.
Professor Banik is here.
So, if there are more questions, they can always ask you in person also later.
Sure.
Thank you. Thank you so much, Manik.
Okay. Thank you, Professor Banik.
You are now in Calcutta?
Yes, last week I joined here.
Welcome.
Yeah, thank you.
Okay, thanks, Manik. We'll now
Sure.